Let's talk about cryptanalysis. And today we're going to talk about a couple extra tools that correspond to the chi-squared tool that we looked at in the previous video. If you haven't seen that, I would go see that. Essentially what we're going to do is we're going to look at within groups methodologies instead of between groups. So remember the chi-squared tool was looking at two different distributions. Well, here we're just looking at one distribution. And so in this case, we're going to look at the index of coincidence and we're going to look at the measure of roughness. What these are providing, they're providing statistics to be able to analyze a ciphertext and determine essentially what ciphertext it is and be able to fingerprint it. So ciphers that are not idealistic are able to give off certain signatures that then allow it to be identified. And that's half the battle, identifying what cipher you're looking at and what encrypted the message. In order to do so, you have to use multiple tools. And these are some basic tools that help you analyze some classical crypto systems. So the first one looks at the index of coincidence, and once again, Practical Cryptography is a very good site. I'd recommend going to it and using it. We're going to be using it just as a baseline to get the theorems and theory, and then we're going to code it on our own. So in this example, the IC later is used to determine the difference between the substitution and the veneer cipher. And what these are essentially doing is you can see there's different fingerprints associated with each cipher. And this is assuming you're still working the English alphabet. If you're working with other languages, these fingerprints might be a little different, but they should provide a reliable analysis and be able to determine which cipher you're working with. So in this example, we're going to work with the index of coincidence first, or the IC. And it's determining the frequency distribution compared to the uniform distribution. And so what it's doing is it's taking the count of the letters and in the ciphertext, and it's taking 1 minus that count, and it's dividing it by the length of the ciphertext times 1 minus that count. And it's then summating or sigma from the bottom to the top of the key span. In this case, we're working with the English alphabet, so we want to be concerned with A through Z. If you're working with a poly substitution cipher, then essentially you could be working with a larger key span. In this case, we're just going to concern ourselves with ASCII. They used 65 to 96. We're going to use 97 to 122. Essentially, it's preference on whether you like capitals or you like lower cases. In this case, we're not going to differentiate too much. And so their widget worked pretty well. It's pretty simple, it's intuitive. What you do is you take the value that it's given. So here's it's clear text or plain text. But you can do it with ciphertext as well and determine the IC. So right now we have the character count or the length is 28, and then the IC or plugging it into this formula for the entire key span is going to be 0.082. We can code that on our end, and if you haven't seen the previous video of chi-square, of the chi-square tool, you should go to it and look at it. Essentially, we're taking frequency distributions from Wikipedia of the English language. Well, they took it from a different website, so our numbers are going to be a little different, but not so much that it's going to cause concern. So here we're just looking at the frequencies associated with monograms or one character. You can always do it with more. It's called n-grams, bigrams, trigrams, quadgrams. Essentially, you can do as many grams as you want. But there's a limit of how reasonable it is. and how much information it's going to actually provide you and how much work it's going to be. So we'll go through a couple of examples for the IC. Essentially, what it's doing is it's taking a message, and this is covered in the previous video. It's taking a message, it's cleaning it, so it's turning all characters that are in the English language to lowercase, and it's joining them together. So take out the spaces, turn the capitals to the lowercase characters, and then you take that and you plug it into the formula, or the IC formula. And in this case, we're going to set up an IC with 0 because it's going to be a summation, so we don't have to worry what the initial value is as long as we account for it. So in this case, we're going to sum through the set of characters within that ciphertext. It could be all the way up to the maximum. So there's a min and max boundary that's associated with. In this case, we're just looking at one specific cipher that's going to only be a key span of 26. But if you're looking at veneer or you're looking at polyalphabetic substitution ciphers, then the key span could be much greater. And so that's something you need to take into account. Here we're going to take the count of the letter in the ciphertext and then plug it into the formula, which is going to be the count times the count minus 1 divided by the length of the ciphertext times the length minus 1. And you sum that, or you add it to the IC, and then return the IC. So in this case, we got 0.012. It's very close to 0.008. The difference really shouldn't be too concerning. Then we're going to start on a second example. Hey there, let's get this site up and running. It shows a IC of 0.009. We're going to try a third one, and here I just typed a bunch of random letters, and what it's doing is it's supposed to be determining the difference between a uniform distribution, and the uniform distribution is so close to this random example that's going to show up as 0. Now, I don't know if that's a numerical underflow or whether it actually is 0, but it's so small that you can say it's pretty much uniform in this scenario. So once again, we're going to derive another within groups tool. So instead of looking at the IC or between groups, we're going to look at within groups. Need some water. Give me a second. So now we're going to look at the measure of roughness. And in this scenario, we can go back to the home page of our IC value on practical cryptography and look at the measure of roughness. So this is saying for the probability of each letter, we want to determine the probability or the frequency of that letter that differentiates it from the ideal uniform distribution or flat distribution. In this case, you're going to take the probability of the letter, and they used E, minus it by 1 over the key span. In this case, we're looking at the English alphabet, so the key span is going to be 26. Once again, if you're looking at different languages or you're looking at poly substitution ciphers, then you could have a large key span. But essentially, you take the summation of the probability of that character and you subtract it by the ideal or uniform distribution that is determined by 1 over the key span. And you sum those, or use a sigma, to then determine what the measure of roughness is. And this is very important to determine how similar it is to English or how similar it is to whatever language you're looking at. So I don't know if you've caught on, but all these different tools have a purpose. So the IC is good for determining different ciphers. The MR is good for determining, what language you used, and etc. So let's go to the coding part of it, the fun part. So the measure of roughness. We're just going to use the 3 examples we used above. And in this case, we provided the ciphertext, and we keep the key probability the same since we're only working with a key span from A to Z. And in this case, we can pre-compute the length so that we don't have to continue to call it in the dictionary. Just easier that way, and it's faster. So in this case, we're going to run through the set of the characters within the ciphertext that don't have to correspond to the entire key span. It's a min and max bound from 0 to the length key span. In this case, we map it from letter to the MR value associated with that particular character. So in this case, you can consider it the count of the letters or character divided by the length minus the key probability, which was a term here, 1 over the key span, squared, to account for positives and negatives, just in case that's smaller than that. And then you add those or sum them together to then determine your measure of roughness. And so in this scenario, the smaller the number, the better it is at determining whatever language you're looking at. So these smaller numbers correspond to English text. And then this is a random text. It shouldn't be very small, and it's twice as large as most of these. So that's 2 tools we can use for within groups, and we have a tool for between groups. And now we're just looking at moving towards linear feedback shift registers and RC4, WEP, WPA, and a few other ciphers that we'll be looking at in the future. I look forward to seeing you on my channel, and please enjoy the videos. Always visit CivCrypto, and have a great day. Bye.